Now for the last speaker of this session, who will be Lian Tao Wang, and who will motivate us with his presentation on what we have learned about Higgs.
Okay, thanks for the invitation, and sorry about the slightly changing the title. So for Higgs, I think after the discovery, I think there are of course we have already made very significant progress in the experimental studies of the Higgs, as we have heard from just heard from the talk before my talk. And but I would also want to emphasize there's still a very long way to go to actually understand the Higgs, and it's so long that the LHC will probably cannot really quite finish that job, and but LHC will be able to do a lot. So for my talk, I won't discuss in details about the results, as they have been beautifully summarized by the talks before me. But I will just try to give you a theoretical perspective. I will focus somewhat more on what to do next, basically. But just briefly, we learned a lot about the Higgs, and it's doing what we think it should be doing. And the Higgs to gauge Bose couplings has been very well established. And we started to even see the Higgs coupling to fermions already. And in terms of agreement with the standard model, we have compared the couplings and in many channels. Very roughly speaking, to a serious impression that the agreement is at this moment is a 10 to 20% level, depending on which channel we are talking about. And so yeah, in this sense, I would say it's a standard model like, and no deviation at this level yet. At the same time, I would say, and this is not entirely surprising, even if you think there are new physics beyond standard model that can modify the Higgs properties. So basically, for the following reason. So if you imagine we have new physics and the couples to Higgs, when we integrate them out, it will induce deviations for the Higgs coupling. Usually, it's coming in the form like this, something like a v squared over the scale of new particles square. And so currently the LHC precision again is about 10%, and this means that if you just do a simple estimate, this means that the new physics I need to generate this size of deviation is about around 500 to 700 GeV. At the same time, we also have a lot of direct search for new physics, and it has basically covered a lot of ground for new physics particles below a TeV. Therefore, based on this simple argument, I would say that some deviation, more like order 1, bigger than 10%, is unlikely. Okay, this is not a no-go theorem, so we still should measure all the couplings. But from a theory perspective, it's not entirely surprising that we have not seen deviations in the Higgs coupling yet. Now, going forward at the LHC, obviously, with lots of statistics and the potential improvement on systematics, we're going to make a lot of improvement in terms of measuring a lot of Higgs couplings, both at the 300 inverse femtobar and the 3 inverse attobar at HLHC. And again, very roughly speaking, this will push all the Higgs coupling measurement down to 4 to 5% level. Okay, this is better than the 10% we have now. And if you again do the estimate, simple estimate I did in the previous slide, and this will reach new physics to about a TeV scale. Okay. So at the same time, I think it's also emphasized by a previous speaker, and LHC is really a Higgs factory. It has made more than 3 million Higgses already, and we'll have 100 times more by the end of the LHC. And this means that Higgs LHC can do more than just do the measurement of those couplings. Especially, for example, it's great for looking for clean yet very rare decays of Higgs. So clean has to be, but mostly because LHC, looking for things at LHC is difficult if it's involving soft jets and so on. But for example, for things like multi-leptons and displaced vertices and so on, these are great. Potentially, we can even think about the reach to 10 to the minus 7 sensitivity in terms of branching ratio. Okay. Now, these are my very rough summary of what are the sensitivities now in terms of doing Higgs measurement and what we are going to see in the future. So these are great, but ultimately we want to use this kind of sensitivities to address physics questions. So let's just briefly remind ourselves what kind of questions we want these kind of Higgs measurement to answer, and where are we right now in terms of answering those questions. Okay. So this is basically coming back to the very basic point that we wanted to understand electric symmetry breaking in the standard model or in nature. And so in the standard model, we have this very simple picture. Right? So there's a max height potential, and Higgs goes to its true vacuum, gets a bad break electric symmetry, gives particles mass. Yeah, so this is all very well understood. Doesn't seem to be too much of a mystery here. And but let me just emphasize that this is a simple picture, but we don't know whether this is the picture or not yet. Okay, and this is what we really know. Okay, we know that there is a symmetry breaking. Okay, so in fact we have known it for a long time. Okay, not just after we see the Higgs. The symmetry breaking is there for a long time. Okay, because W has mass. But the new thing is now we actually know there is a particle with that mass. Okay, sitting around the vacuum. But that's all we know. Okay, but what we don't know is that we don't know how to, for example, where does the mass coming from? Okay, so as a physicist, we wanted to not just know a parameter. We wanted to know how do I understand this parameter? How to explain that? So that we have no idea at this point. Okay, and even at a more basic level, we don't understand what the rest of this potential looks like. Okay, we just know this is a very local feature of it. So this can be sometimes cast as the question of the nature of electric phase transmission. So let me talk about talk more about the question of predicting or calculating the Higgs mass. So in order to calculate the Higgs mass, or more specifically in generating the electric weak scale, so the first question you wanted to ask is that, of course, you wanted to explain it in terms of some more fundamental theory. But the first question is, where is the fundamental theory? What is the scale of the fundamental theory? Perhaps it's the same scale as some other fundamental scale we know that in nature, such as a Planck scale and so on. But if so, the immediate question is, how do I get a number of 100 GeV coming out of a number from 10 to the 19th GeV? Okay, so that would it's difficult to imagine, and it turns out in practice it's very hard. Okay, so if that is just that's the picture. Okay, so this is, of course, you all know this, right? This is the so-called naturalness problem, and that's why also many new physics that is motivated to actually generating the electric weak scale and predicting Higgs mass. The fundamental new physics scale is around T. Okay, this is certainly much easier to imagine that I can have a number of 100 GeV coming out of T. So we do have many ideas in this category. The most famous ideas are probably supersymmetry and the composite Higgs. Okay, so this you probably won't see this very well. So, but this is a prediction of Higgs mass in supersymmetry as a function of stop part mass. Okay. And 125 is on the heavy side. Okay, it's on the heavy side mostly because if you look at this x-axis, again, you cannot see this very clearly. This is starting from 10 TeV and go on. Okay, so in the most simple models, you need the stop to be heavier than 10 TeV to accommodate a 125 GeV case. Okay, and that is too heavy to be a natural theory. So it's well known that that is a problem. And on the other hand, in composite Higgs models, you actually have the opposite problem. For a different reason, but numerically it's the opposite problem. Is that light Higgs 125 seems to prefer a small mass for the top partner, okay, composite top partner. So this has two problems. A is that the composite top partner is really a composite resonance. Okay? So naively, from a strong couple theory, you will say, okay, that should actually be quite heavy, not so far away from the strong coupling scale, which is multiple TeV. But even if you accept that the top partner, this light, has already been constrained a little bit, at least by the direct search. Okay, so these two are very popular, very well motivated ideas that can actually solve our problem of predicting the Higgs mass. On the other hand, they all seems to be having a little bit of attention. So such conclusions is not meant to be, again, not a veto on any of these models. And of course, we have many collaborative tracks to go around. But yeah, anyway, we'll certainly continue to look for these. And by direct search at the LHC, so this stop limit is now around TeV. And so already started making, at least some of us feels a little bit uncomfortable, due to the naturalness of weak scale problem. And this is a search for the top partner, and independent of which model point you are, you see that the region preferred by a light Higgs, which is around 600-700 GeV, has been a bit of a constraint already. Again, you can do fine tuning to get around this. Seems that some of fine tuning is always there. And of course, LHC will keep going to look for it, and maybe there will be a discovery, and the future colliders will certainly continue this quest further. But let me come back to the Higgs coupling measurement, and I wanted to say is that Higgs coupling measurement will also play a very important role in this. Again, if I use a composite Higgs model as an example, so these lines, so this is the current limit from the composite resonance search from diboson, and you can also look for them in dilepton, for example. This is diboson, this is dilepton, and these are the ones that we can ultimately reach at the high luminosity LHC. Yet you see that the current, even the current Higgs coupling measurement, mostly coming from the Higgs to W and the Higgs to Z couplings, already give you an interesting cut in the parameter space. So up above this line is a ruled out. And in the future, in the high luminosity LHC, it will certainly improve because of the improved measurement going from 10% to 5% to these kind of improvement. So there's a nice complementarity between these two strategies. As I said, that many of us, at least some of us, already feel uncomfortable about the absence of any hint of natural physics as a top partner, and there have been efforts in trying to hide top partners, building more exotic models. Here's one kind of it, and in this model, the top partner is not colored. But one of the most prominent signal for the top partner for this model is that the Higgs will actually have more exotic decay mode, where Higgs actually decay into a hidden sector and they come back. So, yeah, so there are even more exotic ideas I don't want to get in too much of it. You can be motivated by some, maybe there's some connection between the Higgs, the tuning of the Higgs mass and the tuning of the Gauss module constant. And maybe we even need to modify quantum field theory at a very low scale. And but both of them, they all leads to either deviations in the Higgs coupling or some new rare decays that of Higgs boson. So let me, because this is a really important point, let me emphasize it again. So what's the bottom line on the naturalness? So we talk about naturalness a lot, and since I'm a graduate student, since Susie is the solution, but it's really a very important question. And it's not really about the cancellation of some divergence and so on that we don't understand, but it's really about the question of how do we actually calculate and predict Higgs mass in any given theory. So we have ideas, but you see that at least the current ideas may not be the right one. So, and in general, I think confusion is good, especially this confusion of this magnitude. It's threatening to even challenge the foundation of understanding of our quantum. It's basically the argument that I just gave is it's basically coming from a very basic understanding of quantum field theory. So that is, if that's wrong, that would be very exciting. But of course, we don't, especially at this time, we really need experimental guidance. And unfortunately, in this case, we actually know where to look. Namely, that whatever you do to address the naturalness problem, the new things that is in that theory at least has to talk to Higgs, and it at least have to, a place where we can guarantee to make progress is to study Higgs very well. So that is what I wanted to really emphasize. And let me briefly come back to this question also about what's the rest of the Higgs potential look like. So this is basically the question whether it's actually coming from a Mexican hat or coming from something more exotic, like you have more wiggles in that potential. And so the first thing you wanted to see is what distinguishes these two pictures. They all give the same VAB, same mass, and is to see whether there is a difference you can see on the third derivative, okay, of the potential. And indeed, if you write the form of the potential, you will see that anytime you have this kind of potential, you will actually have a large deviation in the triple Higgs coupling compared to the prediction of the standard model. So measuring triple Higgs coupling is very difficult. I'm sure many of you know already. And at high luminosity LHC, I haven't seen a very firm projection, but my impression is that perhaps we will be able to do it to some order 1 precision. And future colliders, such as 100 TeV PP collider or TeV ILC, can probably pin this down to better than 10%. So that is still very difficult, but this level of precision, I think we can start to have a picture of whether we do expect that it's the more simple standard, more simple Mexican hat picture, or it's something more complicated. And however, I think this is not the only handle we have. If new physics really modifies electroweak phase transition, it will also generate the corrections to other Higgs couplings. Okay? There's no reason that that's the only thing that new physics does. Okay? In fact, you do expect it generates corrections to other Higgs couplings parametrically at the same order as the triple Higgs coupling. So will be sizable deviations in Higgs Z coupling, for example. But this is something that we can actually measure very well, much better than the triple Higgs coupling. Yeah, this is just giving you examples. Suppose I have a singlet, and I can integrate them out to both generate the Higgs potential correction that's necessary to give you more wiggles on the potential, but also generates a shift in the Higgs Z coupling. Let me not talk about too much. And this is a figure in that model, and all these points are actually give you first order phase transitions. And you see that, since I'm going to focus on LHC here, let me just say that the LHC does not cover all of them, the kind of the size, but just by measuring delta ZH, LHC does high luminosity RGC, we'll be able to see quite a bit of it. The current sensitivity doesn't quite do it, but high luminosity RGC will actually be able to cover a sizable portion of it. You may even see an early indication that the electrical symmetry breaking is unconventional compared to what we used to see. Okay. So in the last 5 to some minutes that I have, let me talk about 6 minutes I have. Let me talk about going a bit beyond to the standard model Higgs coupling measurement that I'm talking about. So in particular, let me focus on the case where the new physics, of course we have all these direct searches for new physics resonance, but what if the new physics resonance is actually too heavy to be produced directly? Okay, so this is just some schematic plot. Imagine there's no rate beyond this. This is some center of mass energy. And the way, in this case, the way the new physics show up was through some of these long tails, some tails of this new physics. So we'll be looking for some of these tails. And particularly, I think a promising place is in the diboson final state. It's very closely related to the electrical symmetry breaking. Almost any new models that that give you interesting to address the electrical symmetry breaking will actually produce something like this, especially those has some kind of a strong couple. Okay? And on the other hand, this is also very difficult, even if it's not rate limited, because there's not a very obvious feature. Usually it's systematically limited, and this is precisely the place where we actually need a lot of systematic improvement on the systematics. So let me just so usually they are captured by these. The effect of such a resonance are captured by these higher dimensional operators. And so why do we think LHC actually have a chance to do this kind of precision measurement? After all, lab has done a lot of precision measurement, has already set very strong limit on some of these operators. So lab precision on new physics usually is at the neo level. Okay, so this is to be slightly more numerically more precise. This is it's probing new physics scale around 2 TeV, okay? Because the correction at the lab goes like this usually. On the LHC, on the other hand, we have we're coming from the same kind of modifications, but we have that advantage that we can actually go to higher energy. So these are non-renormalizable operators. They have become actually more important at higher energy. Okay, so if I still put the 2 TeV here, but if I can now probe energy regime around the TeV, then at the LHC, I don't need to make a per mille measurement, which is obviously not possible, but at LHC, we just need to make a 25% measurement. Okay? Then I can have a comparable sensitivity as lab. Okay? So, of course, this is assuming that there's some standard model signal interference, but without interference, we'll go down to another power of E square over lambda square, and then we really need to make a 5% measure. So let me emphasize again, we need both of them to be true. So there's energy growing behavior like this, whatever signal I'm looking at, and then there has to be interference. Okay. So yeah, let me not go through too much detail, but this is just saying that the standard model background for the diboson final state coming with different polarization configurations with different strengths. And for different new physics operators, we need to focus on those channels that has both has the energy growing behavior, also has a large interference piece with the standard model background. So longitudinal polarization is probably the most useful one. And we do need to tag, in some sense, tag on those polarizations in many cases for the WW final state in particular. Okay, so if you don't tag, then we have to sum all the channels, then the interference effect is not that big. So yeah, this is the energy growing. That's what the signal look like. And so the next question is really where to look. I'm saying that I said that we should roughly aiming at the look for energy regime around the TeV. So there's some simple scaling argument you can make. Let's say for the moment, if I forget about systematics, and assuming that the new physics parameterized by some operator like this, then there's some simple scaling argument you can make that in fact for the dimension 6 operator, if d is equals to 2, in fact it's actually advantageous to look at the lower energy because the s over root b actually increase towards the lower energy. And this is basically because the PDF actually falls very fast as well. So, and of course, yeah, so this is basically what this blue curve says. This is the limit you can set, assuming that the systematic is 0. But of course, this is not the realistic case. If you do start to have systematics, and then the systematics will actually lower your limit, particularly at the lower energy side, because that's where the S over B is small. When the S over B is small, you tend to be dominated by systematics. So in the real situation, it's a trade-off. So both of them, it's a trade-off. You probably wanted to look at the regime somewhere like this. Yeah, so this is just an example. For example, in the WH channel. Okay, so with some assumptions, idealistic assumptions about systematics, but I think. And this is, for example, in this particular case, with our assumptions, around TeV is what you want to look at, and you will be able to probe around the new physics scale around the 2 TeV. And this is some different kind of reach for new physics scale, assuming with some different assumptions about the size of the reducible background, the efficiency you will be able to tag in correlations and so on. Okay. So many of these are probably too idealistic. I mean, this is just put forward as benchmarks. This just shows that you need to reach this kind of performance to be able to reach that kind of new physics scales. And we can also, so this is the figure I showed earlier. So you can, these are the direct resonance searches. So these are the Higgs coupling measurements. And we will, if we're able to actually achieve some of these good measurements of those long tails and so on, we will be able to probe, for example, in one of the operators, you can show that you can see that we can actually also have an interest in them just coming from measuring those operators. Again, complementary to the other probes. Okay, so this is my conclusion. So I think we are, as far, we are, even though a lot of the direct searches for new physics resonance will still go on, I think we are entering an era of precision measurement at LHC. Okay? A lot of data to come, and the Higgs measurement is certainly the prime target. And it's actually a very good target since the Higgs is really a central question in particle physics. We wanted to understand how to predict Higgs mass and understand the nature of electric phase transition. And the current picture is very confusing at this moment. So there's a good opportunity for big discoveries. And LHC will certainly be our guide for the foreseeable future, and also setting the stage for the next steps. Thank you.
Thanks for your presentation. So we're open now for questions and comments. Yes, there is one.
Suppose there are suppose there are extra neutral scalars that don't indicate to TT bar. What do we know and what are the prospects? Actually, generally, because you at the end of the previous talk, you asked about, or you corrected 2HDM2. So in general, why do you not cover to a second doublet and jump to a singlet? Okay. First, if there are neutral Higgs scalar bosons that don't indicate to TT bar,
yeah.
What do we really know, and what are the prospects for the full HLOHC?
So, well, they will show up with TT bar resonances, right? So I think that this has been studied recently by Paul Liu and some other people. So this is a.
I thought that their point, which is not not new is that the TD bar resonance and the scalar channel are very difficult.
It is going to be very difficult, right? So because it has to couple to TD bar by mixing with some double, right? So that is already, if it's a singlet, then I think that there's already a suppression there, right? So then there's rate and so on. So I think yeah, I think the mass rate each will be moderate. Let me just say, I don't know what right. So
I thought what they said was that it's not discoverable.
I think that's a model-dependent statement. Okay, we can see whether if you have an interesting rate into 4 tops, right? TT bar associated production with this, I think that the final state is good, right? So that is that you have a lot of handles, but yeah.
Well, 4 top is long away.
No, I'm talking about the TT bar associated production with the resonance. So I think the rate will be challenging. That depends on the mass of the resonance. Interesting. So I think there certainly will be a reach. It may not be as a so you know for singlet, I think most likely the singlet really decays like a Higgs standard model Higgs, because usually it gets most of the coupling from mixing with the standard model Higgs. So that's the but there is a suppression, right? So there is a from the mixing.
Okay. Are there further questions or comments? But if not, we thank again the speaker and all the speakers. So now we break for coffee. You have an announcement? So please wait.